As the name suggests, a data flow program describes how data flows between operations. Data flow programs are commonly represented as direct graphs. Well, nodes are called operators and represent computation, and ends represent data dependency. Operators are the basic functional units of the data flow application. They consume data from inputs, perform a computation on them, and produce data to outputs for further processing. Operators without input ports, named source, and operators without output ports are called data sinks. A data flow graph must have at least one data source and one data sink. Data flow graphs like this is called logic graph because this is a high-level view of the computation logic. In order to execute a data flow program, its logic graph will convert into a physical data flow graph, which specifies in details how the program is executed. This figure is very high level. Actually, the Flink implements data flow transformation at 4 levels. First, transform from a program to a stream graph. Second, transform from the stream graph to a job graph. Third, transform from the job graph to an execution graph. And fourth, transform from the execution graph to a physical execution plan. After a program is executed, a directed acyclic graph (DAG) or logic execution graph is generated. In addition to the physical graph, the other 3 types graphs we can find from the corresponding Java class in the Flink source code. Let me show you. As you can see, this is the stream graph, and this is the job graph. Also, it's the execution graph. Okay. In order to let you more clearly each level data graph transformation, let me show you what happened between the graph transformation. Okay. Suppose this is our source code submitted into Flink cluster. Okay. The first level transformation from program to a stream graph starts from the source nodes, and each transform operation generated one stream node, as you can see at here, stream node, and the 2 stream nodes are connected by a stream edge to form a DAG. Okay. The second level transformation from the stream graph to a job graph also start with the source nodes. Operators traversed to find the operators that can be changed. As you can see at here, the keyed aggregation and the sync operation have the same parallelism and connected by the forward channel. So both of them can change together. Okay. If any operator cannot be changed, a separate job vertex will be created for each of them. If the operator can be changed, such as the keyed aggregation or sync, both of them change together at first, and then form a new job graph at here. Okay. The upstream and the downstream job vertex are connected by the job edge, form a DAG at the job vertex level. So totally speak, at the job graph level, the operator chaining will happen. After the job vertex DAG is submitted to a task, the nodes are sorted start from the source nodes. An execution and job vertex is created based on each of the job vertex, and an intermediate result is created based on the intermediate dataset for each job vertex. The intermediate result is used to create an upstream to downstream dependency to form a DAG at the execution job vertex level, namely the execution plan. So in short, at the execution graph level, the parallelism assigning subtasks, a subtask split will happen at this level. And finally, the execution graph is transformed into a physical execution plan. Actually, at this physical execution plan level, the subtasks are distributed to cluster slots. For execution, also at this level, specifying how the data exchanged, as you can see, such as the hashi and forward, okay, and the rebalancing, right. Okay, see you next lecture.